Hi, everyone. So welcome to your first online lecture for our online course. We are going to continue into chapter 17 in a slightly different fashion in this section. So instead of reading my material, I am going to have you listen to my material. So while we go through this lecture for the next probably about half an hour, you should definitely have your notebooks open. You should be taking notes. You need these notes both to prepare for your exam that's coming up and then also to answer questions on the short quiz that you will have as part of this section. What I want to highlight about chapter 17 is that we are not studying the whole entire chapter. We are going to only be studying a few key reactions. What we have already studied are the addition reactions. So that was this last weekend. You had an assignment on addition reactions. At the beginning of today's class, so for your online reading material, I had you read just a little bit about the side chain reactions of benzene. What we're going to study right now by video is electrophilic aromatic substitution. So this chemistry, in short, goes by EAS. It's often referred to as EAS chemistry for electrophilic aromatic substitution. Next, and so then this will be homework for today leading into Wednesday's class. We are going to be studying nucleophilic aromatic substitution. Okay, let's go ahead and dive right in. So key fact that I need you to remember is that benzene is not very reactive. So what we have been studying is, yes, of course, this is the traditional way that we draw benzene. We have conjugated double bonds. However, we have looked at the molecular orbital energy diagrams, and what we have seen is, in reality, when we study all of those energy diagrams, all of the bonds around benzene are just partial double bonds. And so really we represent the character best if we were to draw dashes all around. And that is why it is very common that people very simply draw benzene just like this with a circle in the middle. That also represents that we have partial double bond character. Okay, so then this is the key. Our reactivity of benzene is low. It is just not very reactive. So what that means is if we have a weak benzene starting material, and benzene in the first reaction that we're going to study is acting as a nucleophile. And so if we have benzene as a weak nucleophile, then what we have got to do is we have got to pair it with a very strong electrophile in order to do any kind of chemistry at all. That is incredibly important. We have to add a strong electrophile or there will be no product formation at all. Let's get started into the mechanism of what will happen when we have that strong electrophile. So the first step of the chemistry is that our weakly nucleophilic pi bonds are going to attack our strongly electrophilic electrophile. So let's go ahead and draw that out. For the sake of drawing mechanisms, we always begin with benzene drawn in its fully conjugated state, just like this. The electrophile, I'm just going to put E, indicate that it is strongly electrophilic with a positive charge. And so in the very first step of our chemistry, the weakly nucleophilic pi bond attacks the electrophile. And so what results from that attack? So we still have our six-membered ring. We've done nothing to break any of those bonds. We've done no chemistry at the other two pi bonds. They are intact. And then what happens where we have done chemistry at carbon 1 and carbon 2 is one of the carbons gains the electrophile. The other carbon becomes carbocation in nature. Since this benzene is completely symmetric, it does not matter if I add the electrophile to carbon 1 or if I add the electrophile to carbon 2. And so it is just as likely in 50% of my material that the others I could draw just like this. The other 50% I could draw just like this, which actually is the same thing. This carbocation intermediate has a unique name. It is called the sigma complex. And that is because it is a unique structure. So it is a cation in the middle of a conjugated ring. So it has a special name since it's a special kind of structure. Okay, this very first step of the chemistry is high in energy because I am forming a carbocation. But this carbocation is relatively stable. It is relatively stable because it is being stabilized by resonance. So it is important that you remember how to draw resonance. So let's go ahead and practice that together. So if I have my ring, I'm going to add electrophile, I'm going to add positive charge. And so then to go back and make sure that I transfer the structure exactly correct, I have my pi bond here and my pi bond here. Okay, so then what does the resonance look like? So we always draw resonance from where we have electron density to where we don't. When we're doing resonance, we move electrons that are in pi bonds or that are in lone pairs. Here I have a pi bond, and so I move the pi bond to the next bond. And what does that first resonance structure look like? So I have my 6-membered ring. I'm going to add my electrophile. I'm going to add this pi bond to the left. I've moved the pi bond. Now the second pi bond is to the right. And then where is my new positive charge? My new positive charge is right here. Something to keep in mind is that at every one of these carbons, we have one bond to hydrogen. So let me fill in those bonds to hydrogen. This is line angle drawings, and so I didn't need to do line angle drawings at first. And so now it is a little bit more obvious why the lower carbon has the carbocation, because there's only 3 bonds around that carbon. That's why it's a carbocation. Okay, let's draw the next resonance form. So for the next resonance form, I move electrons from the pi bond into the next bond. Let's get that double-headed arrow. Then I still have the bond here. We added my electrophile here. Okay, so now I've moved it here. And so then the positive charge is right here at that location. And so then these are the 3 resonance forms of the sigma complex. So there are always 3. What I want you to notice is that in drawing number 1, we could say that the carbocation is at carbon 1. And then in drawing number 2, the carbocation is at carbon 3. And then in drawing number 3, the carbocation is at carbon 5. So sometimes what is done is that we draw like a summary picture of all of these 3 resonance forms. We have the electrophile at the top. We say that a positive charge is being shared like all the way around, but in one resonance form, it is located here. The second resonance form, it's located here. And in the third resonance form, it is located right there. So this would be like a summary picture of where all of the resonance forms are. What I think is most important as you go back into your own drawings is to just recognize that there's a pattern, that our positive charge is at the 1, the 3, and the 5 position. So that is if we consider the position of the electrophile to be at like carbon 6. Okay, so those are all the resonance forms. So for the electrophile chemistry, the first step is the pi bond attacks an electrophile. In step number 2, we get resonance stabilization. I'll just go ahead and highlight what that resonance stabilization does. Is, let's say this is the first step of an energy diagram. What resonance stabilization is doing is that, oh, I didn't want highlighter. Let's go to a pen, but let's go to a different color of pen. Let's go ink color blue. So what this resonance stabilization does is it lowers the energy of activation so that we form plenty of carbocation. But now let's get into this third step of the chemistry to finish off electrophilic aromatic substitution. And so then the third step is like this. So I have that carbocation intermediate. At one carbon, I have the electrophile. At the other carbon, I have a positive charge. I have a pi bond here. I have a pi bond here. What happens in the last step of electrophilic aromatic substitution is that a base that is present in solution removes the proton from the same carbon as the electrophile. Those electrons between the carbon and the proton move in to reform the double bond. And then our final compound is going to be back to the cyclic conjugated aromatic system with a new electrophile. Okay, so then that is all of the steps. But I've kind of done lots of scribbling. So let's go ahead and remove all of the scribbling. And let's redraw this like all at once. Okay, so I've cleared my page. So let's just draw this chemistry out all at once without any scribbles in the middle. Okay, so to start again, I have my benzene ring. And in the first step, my weakly nucleophilic pi bond attacks a very strong electrophile. One carbon gains the electrophile, the other becomes a carbocation. That carbocation is stabilized by resonance. We have a total of 3 resonance forms, and I can add those plus charges at the 1, 3, 5 position. And then in the next step, I have a base that is present in solution. That base is going to remove a proton from the same carbon with my electrophile. Those electrons move in to reform the pi bond, and I get my benzene ring with a new electrophile added at the end. Okay, and so that is the summary of electrophilic aromatic substitution. So let's look at a figure from your Wade textbook. What your Wade textbook is reminding you is that when we have our benzene ring, all of the p orbitals are overlapping, all the top lobes overlap to create kind of a ring of electron density above the carbons, and then all the lower lobes overlap to kind of create a second ring. But when I use a pi bond to attack my electrophile, my starting material is absolutely aromatic, but what is the nature of this intermediate? And the nature of this intermediate has to be non or not aromatic. And that is because in adding the electrophile to one of the carbons, we have now created an sp3 carbon with 4 single bonds. And so then we are violating, really both the first and second rule of aromaticity. So we do not have conjugation all the way around the ring. And also we do not have a p orbital at every atom in the ring. And so we go from aromatic to non-aromatic in character. This is very high in energy, but it is being lowered in the fact that there is resonance stabilization. However, when we have the base remove a proton, We reestablish the aromatic nature. We form a final product that is stable. Okay, so then this is the figure from your book reminding you about what is happening in regards to the aromaticity of the benzene ring as we move from the starting material to the non-aromatic intermediate back to the aromatic final product. Okay, so let's talk about some key facts in regards to electrophilic aromatic substitution. Okay, so the benzene ring is not very reactive. Okay, so what kind of chemistry can we do? So electrophilic aromatic substitution is much more favorable if we have an electron donating group. If we have an electron donating group that activates the benzene ring to do additional chemistry. And that is because if I have this donator is pushing extra electron density into the ring. That makes the ring more nucleophilic, and therefore that makes it more reactive. And so in this chemistry, we refer to electron donating groups as activating groups. That's how we refer to them. So they are activating groups. But I want to look at this just a little bit more, just a lot like we did with Diels-Alder. So if my donating group is pushing electron density into the ring, which carbons become dipole negative? Okay, so if the density comes into the ring, it would push out like to this carbon. So this carbon neighboring the donator can be very dipole negative. But it is not the only dipole negative carbon in an activated benzene ring. So let's look at another scenario. So the other scenario is like this. My donating group pushes in electron density. That pi bond goes over here, and then that pi bond pushes electron density right here to this location. So this location is also very dipole negative. Okay, so to draw out a summary picture of what I have just said, if I have a donating group adding electron density, I will make this neighboring carbon dipole negative. I will make this carbon on the opposite side also dipole negative. So what we say about electron donating groups is not only are they activators, but they are also ortho and para directors. Because notice how in evaluating where we have the most dipole negative character, it is ortho to the donating group, and then it is para to the donating group. Okay, so activators are ortho-para directors. Okay, so let's do some practice. So let's do a mechanism with an electron donating group. And so I'm going to start with the simplest electron donating group. Let's say that we have a methyl group. So if I have a methyl group bonded to a benzene ring, the methyl group is a donator. It's not a strong one, but it's definitely a donator. And this structure is known as toluene. So benzene with one CH3 is toluene. So toluene is activated towards chemistry. And let's be specific, it is activated to electrophilic aromatic substitution chemistry. And we would say that the CH3 group is an ortho para director. So what can the chemistry look like? So there's two. What that can mean is I can take this neighboring pi bond. This neighboring pi bond adds a new electrophile. I would get this sigma complex, CH3, with my electrophile, so it's added to that ortho position. If I added the electrophile to the carbon on the right, then this needs to be the carbocation. And in the next step, there is going to be some base that is present in solution that can remove the proton. Those electrons go back in and form the pi bond. And so then my new final product will look like this, with the electrophile in the ortho position. But what other chemistry can occur? And the other chemistry that can occur is like this. I'm going to do the parachemistry. And so what the parachemistry would look like is that it would be this other pi bond that adds to the new electrophile. I get a sigma complex intermediate. That pi bond remains, that pi bond remains. I have my CH3. I add my new electrophile to the para position. That means that this other carbon becomes the carbocation. And then in a final step, I have some base that is in solution. It abstracts the proton. Electrons move in to form the pi bond. And so here is the look of my final product. I have my CH3 and then my new electrophile in the para position. Okay, so that is the mechanism on if I have a donating group that is bonded to my benzene ring. So there's something else that I want to highlight here. And that is with the ortho-para director, that chemistry happens because the most dipole carbons, dipole negative carbons, are at the ortho position, and the most dipole negative carbon is at the para position. But what I want to highlight is let's look at the carbocations. So notice that the carbocations that I form, or that I can form when I do this ortho-para chemistry, are really nicely stable cations. Remember, there's a 1-3-5 relationship, and so I have cation here, and then if I were to draw all three sigma complexes, this would be the locations of all the cations. And so what is especially great about that carbocation right there? I'll give you a second to think about it. So again, what is especially great about that carbocation? What is its like unique character? And the answer is yes, you are right. So what's unique is that that carbocation is especially stable because it is tertiary in nature. Okay, so I did chemistry with a very dipole negative carbon, and I get an intermediate that has tertiary characteristics. Okay, let's come down to this second reaction where I did chemistry at the para position. Okay, so I do chemistry at the para position because it is the most dipole negative. Let's jump over to the sigma complex again. And actually, I am going to go over to a different color of pen. Let's choose blue again. That's kind of a nice, brilliant color. Actually, I might have gone to black. So if there's a 1-3-5 relationship between all my cations, I would have a cation here, and then in a second resonance form, a cation here, and then a third resonance form, a cation here. And so now what's especially great about this collection of intermediates, these cation intermediates? And yes, you have it right again. In this collection of cation intermediates, I also have a nice stable tertiary carbocation. Okay, so what this means is that there are two reasons why we do activated chemistry at the ortho and para positions. We do this chemistry because at those locations we have the most dipole negative carbons, And also at these positions, we have the most stable carbocations that can result. So two reasons why we do electrophilic aromatic substitution at the ortho and para position. Okay, so with that, I am going to go ahead and stop this video about the mechanism with an electron donating group, keeping this video short. And in the next video, we will look at what happens instead if we are doing a mechanism with an electron withdrawing group.